Alright, in this video we're going to be talking on hyperconjugation. Now, unlike normal conjugation system which involves PCs with a sigma bond found between two pi bonds and the delocalization of pi electrons, an example of this normal conjugation that we all know is benzene. Now we all know benzene. Benzene has a ring structure with a sigma bond found between two pi bonds, and the pi bonds are delocalized. That is, it has two resonance form. That means this structure can be in resonance with this also. This is benzene. The electrons are not stable, they move around. That's what I'm actually talking about. Unlike that normal conjugation, hyperconjugation is a type of conjugation which is dependent on the presence of at least one hydrogen atom on the carbon that is alpha to the unsaturated carbon system. Now, actually, what I mean by this is that hyperconjugation is not dependent on the double bond, or what should I say, the double bond or the sigma bond and the pi bond. It's mostly dependent on the sigma bond, but it can also occur in the pi bond. An example of this is, let's say, CH, double bond CH2. Now, from my definition, I said hyperconjugation is a type of conjugation which is dependent on the presence of at least one hydrogen atom on the carbon that is alpha to the unsaturated carbon system. Now, this carbon system above here is the unsaturated carbon system. Let me use a different color for that. This is the unsaturated carbon system, yeah. Now, the alpha carbon, okay, the alpha carbon, this is the alpha carbon C. Now, I said at least one hydrogen atom must be present in the alpha carbon for the system to undergo hyperconjugation. That means two alkyl group can be present, at least one hydrogen needs to be present. If one hydrogen isn't present, that system can't undergo hyperconjugation. But if two hydrogens are present, it can actually undergo hyperconjugation. If two hydrogens are present, it can actually undergo hyperconjugation, something like this. If three are present also, hyperconjugation can still be undergone. If three are present, sorry, that's meant to be a hydrogen group. If three are present, hyperconjugation can still be undergone. Now, if we look at this is the alpha carbon. Now, this is the unsaturated carbon. Now, I said, from my definition, hyperconjugation is a type of conjugation which is dependent on the presence of at least one hydrogen atom on the carbon that is alpha to the unsaturated carbon system. Now, we know conjugated systems, they always undergo resonance. That means they'll have like two different forms or many different forms, actually called canonical forms. And like the average, or what should I say, the sum up of all those forms are called the hybrid form. Now, also in this hyperconjugation, it's going to have different resonance form, just like the normal conjugated systems we are all familiar with. So let's go on. For hyperconjugation to occur, at least one hydrogen or more hydrogen atoms must be present in the alpha carbon. I've given that point earlier. This is just like emphasizing on it. There are three types of hyperconjugation. Now, this is something we need to take note of. There are three different types of hyperconjugation. That is three different, what shall I say, perspective of hyperconjugation that we all need to familiarize ourselves with. The first one is sp2 hybridized carbon with at least one hydrogen atom attached to the alpha carbon. I'm actually going to show you like the structural representation of all this hyperconjugation later on in the video, but now let me just give you the types. The second one is a free radical carbon with at least one hydrogen atom attached to the alpha carbon. And the third one is a carbocation carbon with at least one hydrogen atom attached to the alpha carbon. Now, this is the first one, the sp2 hybridized carbon with at least one hydrogen atom attached to the alpha carbon. Now, note this. the hydrogen still maintains its relative position, because I'm actually going to be showing you resonance form of all of this, and you have to know this: the hydrogen will still maintain its resonance position, and the greater the number of hydrogen found in the alpha carbon, the greater the number of canonical forms it's going to have. I've talked about that point earlier, but I'm just going to talk about it later. Now, the first type of hybridization we have, I told you that it's going to have two different resonance forms, and I'm going to actually show you those resonance forms. This is for at least one hydrogen atom. You can actually decode the rest of them because I'm trying to save time. So I'll actually only give you one example, but with that example, I'm expecting you to actually decode the rest of them. So now, like I said, from this, an sp2 hybridized carbon, we all know sp2 hybridized carbon, it must there must be a double bond present between the functional group. The double bond is actually the functional group, so I have CH double bonded with CH2. Now the alpha carbon is attached to the functional group. Now this is the alpha carbon. Okay, this is the alpha carbon C. This is the alpha carbon. I just want to put an alpha sign at the top of it. Now this is our group. This is our group. Now this alpha sign might affect my. So let me put my hydrogen group here. Then let me put my alpha here. Okay, that's good. Now this is what I mean by the unsaturated, the sp2 hybridized carbon with at least one hydrogen atom attached to it. This is the one hydrogen atom. This is it. Now this is the sp2 hybridized carbon. Now, like I said earlier, it's going to have, according to this, let me just give you a hint. When it has one hydrogen present, it's going to have two different canonical forms. When it has two hydrogen present, it's going to have three different canonical forms. When it has four hydrogen present, when it has three hydrogens present, it's going to have four different canonical forms. Actually, there are going to be three different canonical forms and one hybrid form. So if I just sum them up, you're going to have four different forms. So now, let me just draw the two resonance forms for both of them. Okay. Now I have my CH double bonded with CH2. And this is my alpha carbon. Now this is in resonance with this other form. Now if I'm actually going to be showing the mechanism or something relating to that, so you won't get confused, let me just actually draw this bond well, because that's the important bond. Now you see this bond between the hydrogen and the carbon, it's actually going to break homolytically. What I mean by that is it's actually going to be transferred here. Now we all know something about resonance, that resonance occurs between, for resonance to occur, a sigma bond must be found between two pi bonds, or that condition must be met. Now for this bond to actually drop down to this bond between the carbon and the unsaturated functional group, it means that this bond here actually joining the two functional group will actually need to go up and go to this carbon again. I hope you understood what I'm saying. Now look at this. The first one, the bond holding the carbon and the hydrogen, will actually break heterolytically, will break heterolytically, and it will actually come down to this carbon, or should I say to the alpha carbon, the bond between the alpha carbon and the unsaturated system, and the bond between the two functional groups of the unsaturated system will actually break too homolytically, because what should I say, two double bonds can be found in close position. They have to be a difference for it to undergo resonance. So this bond will actually move to this first carbon here. Let me just call this carbon 1, and carbon 2 will actually move to carbon 1. So it's going to have, this will be the second resonance form, C. sorry, C. Now the hydrogen will just be here. There's an R group here, an R group here, a double bond here, CH, double bonded with CH2. Now I need to get you back to a road I said here. Now I said the hydrogen still maintains its relative position. That is very important here, because if you look at this, there's no bond between the hydrogen and the, what should I say, should I just call this like the group, the functional group. There's no bond between the hydrogen and the functional group, but still the hydrogen maintains its original position. It does not just like fly out because it doesn't have a bond between both of them. Instead, its position is maintained between the carbon and the hydrogen. The position doesn't change at all. And now these two forms, they'll end up resonating. This will actually, from this is meant to, it's meant to be like a negative charge here, and this double bond actually is not meant to be here. Sorry for that error. Double bond is not meant to be there, and there's meant to be like a negative charge there, because the electron from this will actually move to the top of carbon number 1, and the hydrogen maintains its original position. Those two things that I just said earlier that are really necessary for you to take note of, because if you don't actually take note of all of this, you can actually end up missing every single thing. Now this hydrogen, just keep it as it maintains its original position. Now there'll be like to be resonating like I said before, and we have to like actually draw a hybrid form of both of them instead of just a hybrid form to show how the resonance and everything keeps maintaining its original position. So I'm actually going to draw the hybrid forms. These two forms actually here, they are called the Cano sorry they are called the canonical forms. These two forms here, they are called the canonical forms. And now I'm actually going to draw the hybrid form. Like I said earlier, there are different canonical forms. Now I said there are two different canonical forms. This is the first canonical form, this is the second canonical form of like an unsaturated system with one hydrogen present. I said I'll give it, before I draw the hybrid form, let me just give you this. For when there is one hydrogen present, one H present in the alpha carbon, we are going to have two different canonical forms. Two canonical forms. When there are two hydrogens present, we are going to have three canonical forms. When there are three hydrogen present, we are going to have four canonical forms. And that's what you're meant to take note of. You can actually decode it by actually just taking the mechanism. Let me just like give you the hybrid form, then actually I can give you an example on another canonical form. Now the hybrid form is not actually going to be hard. This is where my hydrogen is. This is where my alkyl group is. This is my alpha carbon. This is my unsaturated system, double bonded with CH2. Now actually what you just need to do is just like actually draw a line across this. You can impute your negative charge, and that's just like your hybrid form. It's showing that this line is actually showing it's resonating. This electrons actually resonating between both of them. You can actually remove this bond here and just show it like this, that this electron here actually is resonating between both the hydrogen and the carbon 1 of the unsaturated system. Now I also want to give you another example of resonance of an alpha carbon with 2 hydrogens present, so you can actually decode the third one. So I have something like this: C, H, H, and R, double bonded or single bonded, not double. Single bonded with C, double bonded with CH2. Let me include my H here. Now I said it's going to have three canonical forms. Let's call this canonical form 1, and let's get canonical form 2. The canonical form 2 will, let's just say it's going to involve this first hydrogen. This first hydrogen comes here, this bond also goes here, and that's the first canonical form. So I have C, my H maintains the original position, this still maintains this, my R still maintains this position, C double bonded with CH2, and include my hydrogen here, and then my negative charge. This is my second canonical form. If I put it that way, this is my first, this is my second, and then my third canonical form will be this second hydrogen here. It's out. Let me just show you. C double bonded with CH2. This contains the hydrogen, and this hydrogen, my alkyl group. Now this second canonical form won't involve this hydrogen, to involve this second one. This second hydrogen actually move here, and then this actually moves here, and this will be our third canonical form. Now at the end of the day, we'll find out that the bond here actually breaks. And a new bond is formed at this position. Something like this. This should be our last canonical form, and that's like all for sp2 hybridized carbon with one hydrogen or more present, at least one hydrogen present in the alpha carbon. Now the second one is a free radical carbon with at least one hydrogen atom present in the alpha carbon. Now we all know a radical, but let me just give you like a radical is like an unpaired electron. When an unpaired electron is present in an atom, it's called a radical atom. Now a radical carbon will be like an unpaired electron present in like, or what should I say, a single electron present in the carbon atom. So I can actually give you a structure. So something like this. Something like this. CH2. It's usually represented by dots, something like this, by dots. Then CH R, sorry, there's a bond between these two. H, then this is my bond, then this is my R group. Now this is my radical carbon, a free radical carbon. Now actually what is going to be alternating between these two bonds is actually this radical. It's not actually going to be this bond. This bond actually have to break homolytically to form a radical, and that's what's actually going to be alternating. So let me actually just like give you the resonance form of this. So I have my CH2, and this is my radical. This is my C, this is my alkyl group, my second alkyl group, and my hydrogen. Then this will be like in resonance with this other form, CH2. I'm actually going to show you what's going to happen here, but let me just finish drawing. R, and my H. Now actually what's going to happen is that this radical present here will actually come down here to try and form a double bond between these two structures. And what's actually going to happen here is that the bond between the carbon, the alpha carbon, and the hydrogen is actually going to break homolytically, and it's one electron is actually going to go to the hydrogen, and the second is actually going to go to this double bond, and it's going to aid in the formation of this double bond. That's this second double bond. If I may give it a different color, this second double bond is actually going to aid in the formation of that second double bond. And at the end of the day, we'll find out that it's as if this radical actually moved from this position to the next and went to the hydrogen position. But meanwhile, it broke homolytically, and we'll actually see this radical is going to be alternating between the hydrogen atom and the what should I say, the functional group carbon. And that's like the free radical carbon mechanism. So the third one, like I said earlier, a carbocation carbon. What's a carbocation carbon? A carbocation carbon is a carbon with a positive charge, if I put it that way. For an element to have a positive charge, it must actually lose electron. It must be electron deficient. That means a carbocation carbon is actually electron deficient. Now, like earlier, what's actually going to be alternating? The first one, that is for my double bond, or what should I call it now, my unsaturated carbon system. What is actually alternating is my double bond. The second one, what's actually alternating is my radical. Now the third one, what will actually be alternating is my positive charge. Now look at this. Let's say CH2 C. Now for this to be called the carbocation carbon, we all know that carbon is normally meant to have like 4 bonds, but now if we look at this structure, we are only seeing 3 bonds. The bond between the 2 hydrogen and the bond between 1 carbon. That means an electron has been lost. So it's going to have a positive charge. Looking for that electron, that is actually what it's talking about. Now this is my carbocation carbon, and what I said earlier, what is actually going to be alternating is actually my positive charge. Nothing else, just my positive charge. So let's go on. Now I'm going to be drawing the 2 resonance form of this. So I have CH2 with my alkyl groups and my hydrogen. Okay, this is alternating with my C. This has a positive charge. Now, let me just keep going. What's actually going to happen is that this bond between the carbon and hydrogen is going to break homolytically again. And when it's actually going to break homolytically, it's like as if it's donating the electron. The carbon and the hydrogen bond is donating the electron, so as to, what shall I say, annul this positive charge. Yeah, and when it's donating the electron, the hydrogen ends up with a positive charge. That is, the hydrogen is electron deficient. Sorry, excuse me. The hydrogen is electron deficient, and so we are going to have something like this: CH2 and therefore the hydrogen will have a positive charge. It becomes electron deficient, so it's not as if this positive charge here, as the electrons, the paired electrons, were actually moving to form a double bond here. This positive charge actually moved to the hydrogen, something like that. If we get how the mechanism is going, that's what it's just actually going to show us, and that was actually telling us it's not as if it's one complex form or something. Actually, hyperconjugation is easy. It's just like normal conjugation system, but instead it's dealing with sigma and pi bond, and it's mostly involving hydrogen. If there's no hydrogen present, hyperconjugation can never occur in a structure. That is just something you need to know. Once you see hydrogen and they ask you, maybe, can this structure undergo hyperconjugation, and hydrogen is present, yes, that will be your answer, because it's the hydrogen that's actually donating or actually receiving an electron. So thank you for watching this video. Please like and subscribe to my channel. Thank you once more.